Okay, so we were talking about 802.3 medium access control, so CMSA CD, CD for collision detection. And for collision detection, it's important that the frames have a minimum size, minimum duration. And for with a little bit of calculation, back of the envelope calculations here, for 10 megabits Ethernet, it was concluded that we need a frame which is at least 50 microseconds. So if we want to transmit an even number of bytes, 64 is a good number. So 64 bytes is 51.2 microseconds, and then we should be okay. All right. And the reason why we want to have a minimum frame duration is because if we have a situation like this, if you remember from the previous lecture here, we have these time and space diagrams where this is think of this as the cable, and we have station A, B, and C here. If A starts to transmit at this point in time, then it takes a little bit of time before that transmission reaches C. So C has no way to detect this ongoing transmission until this time. And it could be like C starts to transmit during this time, and we will have a collision. And this collision needs to be detected. And it's easy for C to detect the collision here, because it was the last node to go in. But we also need A to know that a collision has occurred. And therefore, A needs to keep on transmitting until the time that another frame can come in here. And that time here is twice the propagation time. So if the frame was shorter than this, so suppose that the frame ended, say, here, this was only the frame, then there's no, by listening to the medium here, a collision is never detected, right? Even though a collision certainly occurred here for B. Okay, so for collision detection, we need a frame which is greater than twice the propagation time. And therefore, for Ethernet, 10 megabits Ethernet, it has to be at least 64 bytes. Okay, now back to this random backoff. So when do we do backoff? Backoff we do, yes, question?
Assuming if the system could send the bits faster, the frames has to be increased.
Number of bytes, yes. Okay, so the requirement is on time. So the frame duration in time needs to be a certain amount. In here, 50 microseconds. Which means that if we transmit with more than 10 megabits per second, the frames needs to be more bytes. Correct. Yeah. Okay, so back off here. Remember what happens here, that if I'm on a CSMA CD network, I have a frame to transmit, which means that I go out and listen to the medium. If the medium is busy, then I wait until it becomes idle, and then I transmit. And then I listen to the medium until, and listen for collisions. If I detect a collision, then I stop to transmit and back off. Okay. So when we're in back off, that means that we have detected a collision, which means that I and at least another node is now trying to transmit at the same time, which means that I and all other nodes needs to wait a little bit before we try again. Okay, so the random backoff time is R times T slot. And R here, the integer R, is uniformly distributed between 0 to the number 2k minus 1. Okay, so K, what is K? Well, K here, we see that that determines the size of the selection window. So if we look at what R could be, or the backoff time, it can be at most R times T slot. Okay, and R is the maximum R can be is 2 to the power k minus 1. Okay. So the interval for the back-off time, the size of that selection window, depends on how many retransmissions we have done. It depends on this factor k. So in particular, what we do here is the following, is that suppose we have tried to retransmit the frame n times, okay? Then, where n is some number between 0 and 16, then k is chosen to be the minimum of n and 10. Okay, so that's a fairly complicated way to say something rather simple. So if we want to see what this is, let's draw here what k can be as a function of n, which is the retransmission attempt. And then k is the minimum of n and 10. Okay. So for n equals 0, then k is equal to 0. It's not so important. But then for n equals 1, then k is equal to 1. Right? For n equals 2, k is equal to 2. And nothing really exciting happens until n is equal to 10. Then k is equal to 10 as well. And then after 11, 12, up to 16, k does not change, it's still 10. And actually after the 16th retransmission try, then the Ethernet gives up, right? It just said, you know, I tried now 16 times, something needs to be really badly happening here. Maybe there is a cut on the cable or something like that. So we just give up on that frame. Okay. Back to here. The actual selection window is we see exponential in k, so it's 2k to minus 1. Okay, so so when k is equal to 1, what is 2 to the k minus 1? 2 to the k is 2 to the 1 is 1, minus 1 is 1, right? So which means that the back-off time here, r, could either be 0 or 1. That's the possibility. So either we wait 0 time slots or 1 time slot. These are the only possibilities. When k is equal to 2, then 2 to the k is 4, minus 1, so that's 3. And that means that r is equal to then 0, 1, 2, or 3. These are the possible values of all three. Okay, now in the third retransmission event, then 2 to the 3 is 8, so now we have 7, which means that r could be 0, 1, 2, up to 7. So we see that the possibilities for what r could be, the selection interval for r, increases exponentially in the k parameter, and k is essentially equal to n, where n is the retransmission event, until we hit when k is equal to 10, then 2 to the k minus 1 is 1023, meaning that r could be 0, 1, up to 1023. Okay. So we see here that as the retransmission event, as the number of consecutive retransmission events increases, the value of the possible values of r increases also quite a lot, and that is basically to spread out the retransmission events among the users. And the rationale is the following, is that if we determine that the collision has occurred, the first time it occurs, okay, the only thing I know then is that I transmitted and somebody else. Or it may be several else. I don't know. It was at least one that transmitted at the same time as I did. So then I and all other nodes selects then a backoff time. So maybe I get 0 and somebody else gets 0, somebody gets 1 and so forth. So the probability of collision is pretty high here. It's actually 1/2, right? So, and or if we have only 2 nodes, but if we have 4 nodes, then the probability of another collision is quite high. So then if I get another collision, it means like, okay, so now I got 2 consecutive collisions. That probably means that there are more than 2 people trying to compete for the channel. So then I back off a little bit longer, or at least the selection interval of backoff time increases a little bit. And then if there is a third collision event, then I say, okay, maybe there's quite a lot of transmission nodes that wants to transmit. So then we need to spread out our retransmission events even further and keep on going that. And if we are 1023, there needs to be a bunch of nodes which are trying to transmit at the same time if there should be a collision. But it could happen, right? Okay. And of course, we would like to be not to select a longer backoff time than necessary. So that's why we start small and then end large. Because if we have long backoff times, then the utilization or delays is bad. Okay. So we also said this, that the system will not attempt more than 16 retransmissions. After that, it basically gives up. At high load, the channel activity cycles basically is like this, that if one just listened to the medium, what would we see? Well, we would see that we see a frame transmission. And then during this time, any other node that would like to transmit at this time, that goes in like maybe a blue user here and a green user here, say, they will wait until the end of the frame. And it takes about t-prop seconds before they have detected that there is an end of this transmission. And all the nodes which became active during this will then start to transmit. So in this case, there will be a blue frame and a green frame. And they will overlap a little bit like this. So there will be a collision. The blue and the green user will detect this and back off. But if there is also a red user here, it could be like, for instance, that there will also be a red frame overlapping like this. And then at this time, some say that the green and red users got back off time 0, then the red and the green frame will overlap like this. And then this will continue until one of them wins. Maybe it's going to be like this. And then the green frame is transmitted. And we keep on going like this. So we have a frame transmission. There is a bunch of these unsuccessful attempts to capture the channel until one node captures the channel and then can transmit the frame. So it's like this. Frame, contention, 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 and these all resulted in collisions, and then one user won the channel, and then keeps on like this. Okay. Right. So that's a little bit about the MAC protocol for CSMA CD, the 802.3 version of this. Okay. Let's look at the frame. How does that look like? The MAC frame? Well, it consists of some payload. And this payload here is then the LLC PDU. Okay, so this is the protocol data unit that we got from above, or the service data unit that we got from above, which is the LLC PDU. We then, on the MAC frame, we need a preamble and an SD here. And the preamble is here in order to synchronize the receiver. The SD here is to say that that's the end of the preamble. So the preamble is 7 repetitions, so this 10, 10, 10, 10. So you keep on sending ones and zeros for a while. And then at the end, we get this SD field, which is 10, 10, 10, 10, and then 1, 1. Okay? And then when the receiver sees 1, 1, it understands that, okay, the next bit that comes is the first bit of the destination address, which is 6 bytes long. And then there is a source address of 6 bytes. These are the MAC addresses. And then there is a length field, and the length field tells us how long this data field is, okay, because it could be of varying size. It has to be at least 46 bytes and at most 1500 bytes. These are the limitations. And it needs to be 46 bytes here, because if it's 46 bytes exactly, then this frame from here to here becomes the 64 bytes, which is the smallest allowed for Ethernet, for this collision detection to work. Now, if this information that we got from above is less than 46 bytes, then we put in some 0 bytes at the end to make this to here at least 46 bytes. So the pad field here could be empty also. And then everything is then, we have a frame checksum here, which is a CRC 32 check bits. Okay. These addresses here, destination addresses, if we look at them, there could be 3 kinds. One is a unicast address, which means that it addresses one network interface card, one exactly. So it has one MAC address. And in theory, a network interface card has a unique MAC address. So it's like your personal number is unique, right? You get that when you're born, and you have that for your entire life, and nobody else has it. Okay. It could also be multicast, which means that it's addressed to several network interface cards. And this is something which is somehow configured. But, we form these multicast groups and so forth. We won't talk much about this. But we also need a broadcast address. And that's the address field of just ones, all ones. And that means that this frame should go to all network interface cards which are attached to this medium. And we need that for protocol purposes, as we will see later on. Okay. The length field is the number of bytes in the information field. It's maximum 1500 bytes. The pad field adds 0 bits in order to make the frame at least 64 byte long. And the FSC, the frame checksum, is paired bits of the 32 bits CRC that covers the whole frame. Okay, so it starts by, so the CRC starts to be calculating from the first bit in the destination address until the last bit of the pad field. Okay, so that forms the CRC bits here. So we don't protect the preamble here. It's not needed. Because the preamble is already known what it is. It's always like that, right? It carries no data. Okay, multiplexing. That is how to know which protocol that we are using. It's easy for 802.3 because all Macs in 802.3 has the LLC above it, so there is no multiplexing needed for the Mac. But the LLC could then support IP and other protocols. So, but that's encoded here. Okay. Now, the actual first Ethernet that came out is almost identical to the 802.3 frame with one difference. It has exactly the same type of frame, except instead of having a length field here, which tells us how long this is, we have a type field. And the type field tells the receiver what protocol is above Ethernet. Okay. So DIX stands for Digital Equipment, Internet, Xerox, and they jointly drafted this Ethernet specification back in the 70s. The type field is used to identify the upper layers, which is above Ethernet in their version, right? In the IEEE version, it's always LLC. In the DIX or Ethernet 2 frame, we could have different protocols directly over Ethernet. There is no LLC over it. The type field starts at this number, 0600, and in hexadecimal. And this is greater than the maximum value of the 802.3 length field, which is 1500 in decimal, or 05 DC in hex. So 05 DC is less than 600. So a network interface card that receives a frame can look at the field, these 2 bytes, and understand whether it's a type field or if it's a length field. If whatever 2 bytes we have here in the frame is less than 1500, we know it's a length field. If it's above 1500, we know it's a type field. Okay, so the receiver can distinguish between an 802.3 frame and a DIX2 frame. Okay. Was that reasonably clear? Right. So on an Ethernet, we can have both 802.3 frames and DIX frames at the same time. And the receiver can figure out which frame it is, which type of frame it is. All right. Physical layers for 802.3, there is a bunch of them. And one is beginning was this coaxial cable. And then it was a thick and thin coaxial cables. These are rarely used today, right? So they are more or less obsolete. So today, what is used is this twisted pair. So here is a twisted pair cable. And if you want to look at the, can you pass these along? So here's the inner of a twisted pair cable. It consists of twisted pairs of cables. Okay, so that's why it's called TP. And there's 4 of those. Okay, so today we connect Ethernet hubs and switches. So what is a hub? Well, a hub is where we have several Ethernet connections into a device which electrically connects all these devices together. And this should be then in contrast to a switch, which is what's passed along here, where you plug in your cables into the switch, but they are not electrically connected to each other. They're connected into receivers, transmitters, which can buffer frames inside the switch. Okay. The drawback with this type of device is that whatever frame that goes in here also goes out on all other cables here. Okay. Even though it might not be destined to any of these. While in a switch, a frame that goes in gets switched out onto the right cable, okay? And they are electrically isolated from each other. So when we have a hub here, we can potentially have a lot of collisions because we connect a lot of devices to the same electrical cable, if you like. But if we have a switch, then we can separate these collisions. So we can essentially have more users on the LAN without collisions. So we move the collision problem into a buffer management problem in the switch. Okay. So this is what's used today, right? There are very few of these around. So from 10 megabits, there was 100 megabit Ethernet. I won't talk much about this, but basically it's the same frame format, same basic interfaces and same protocols. Now, there was a question about this. The minimum frame size was 64 bytes when we had 10 megabits. So what happens if we go and we 10 double the data rate? Then we need to increase the minimum frame to 10 times 640 bytes. Okay, so that's one solution. Another solution is to say that the maximum propagation delay has to be reduced. Okay, so that's what that was actually what was done here. One basically said we can't have as long cables if you want to use 100 megabit Ethernet. So then we reduced the propagation time, and we're still okay with 64 byte frames. There were still hubs but these bus topologies and the coaxial cable was disbanded at this time. Gigabit Ethernet. Here we can reduce basically the maximum length here, because then the LAN became too small. So then the slot time was increased then to 512 bytes, okay, instead of these 64 bytes before. So small frames then has to be extended with this pad field to be at least 512 bytes. There is some other stuff that was done here. So frame structure was preserved, but basically we have no more CSMA CD because everything, there is no need. If you have the switch there, where is it? Ah, okay. So if I can have the switch. So for 100 megabit Ethernet, we all use switches here. So on this cable, there's only one device, this device, which is here, and the receiver here. So there is no competition for this cable. So there is no need to have a medium access control for this. Okay, but nevertheless, it was still there in the standard, but it's not used. Then for 10 gigabit Ethernet, then this CSMA CD was officially disbanded. And then we also have a lot of these optical interfaces, so optical cables instead of these electrical ones. Okay, and then I guess maybe there is also a 100 gigabit Ethernet now. I don't know. But Ethernet has evolved then from this coaxial cable, which was a shared medium, until a type of frame structure that we use together with switches in order to provide LANs. Okay, so then why did we spend a lot of time on this medium access control in this course? Because it's not used. And the reason for that medium access control is still super important on wireless. So for Wi-Fi, for instance. Okay, so it still needed to be there. Yes.
Doesn't it use any kind of medium access control?
In here? No, not really. So whenever this station has a frame to transmit, it listens to this cable, which is silent, and then transmit. Okay, because there is only this is full duplex also, so you can transmit data this way and this way at the same time without interfering. So when you want to transmit, you listen to the channel, but since you're the only transmitter, yeah, you always get the channel. Right. So there is no medium access control problem here, even though the protocol is still there. You know. So what happens then is that there is a bunch of frames coming into this, and it's the duty of the switch in order to buffer them and then send them out on the right ports without any further collision. Of course, you can have buffer overloads like this and lose frames inside here. That's possible. But that's more like a buffer overrun problem than a medium access control problem with collisions. Okay, so we want to connect LANs, and we do that by doing this. We can have one switch, we can have several switches, and we connect them together and form bigger structures, right? So how does that work? Well, we can connect LANs in 3 different ways. We can use repeaters, which is basically electrically connecting cables together, so hubs or repeaters. And this is connection on the physical layer. Okay, we connect the physical cablings with each other. We can also use bridges, or LAN switches. This is a LAN switch. So this could be either a link layer device or a medium access control device. And we'll see the difference in a second. And we can also use routers, which is basically routing from LAN to LAN. So it's bigger networks. Repeaters are simple, doesn't scale very well. And bridges can be used then to make the scaling better. We will see that in a second here. So suppose we have now two LANs here, one here and one here, and we want to connect them together. So a end device on this LAN would like to talk to an end device on this LAN. Okay. So what type of LAN is this? Well, suppose it's a one of these, a wired Ethernet. So it's a 10x T physical layer on below CSMA CD 802.3 MAC layer. And then we know there is an LSE on top of that, and then there is a network layer here, maybe IP, I don't know. Okay. Suppose this IP layer would like to talk to the IP layer here. How can we do that? Well, we send out a frame over this, and then it goes into this bridge, which is a bridge between this LAN and this LAN. So this bridge device needs to talk the language of this LAN, which is 10x T, and then it needs to talk this medium access control language, which is CSMA CD here, and then it goes up to this LLC layer. And here it can go over to this and then start to talk the medium access control and physical layer, which is on this LAN. So maybe this is a Wi-Fi LAN. Maybe it's 802.11a physical layer, and then it's a Wi-Fi MAC here. So then the frame goes up like this, and then goes down like this, and so forth. From the network point of view, it just sends frames, IP packets. It didn't know it went over Ethernet and then Wi-Fi. It's hidden, right? And this box here is also kind of magic in the sense that it connects two different technologies with each other, two LANs. Right. So multiple network layers can be supported with this link layer bridge, and it can handle then differences in frame formats, data rates, maximum frame length, and so forth. So there's a bunch of processing that needs to be done here in a way. And it's easier then, of course, if this LAN and this LAN is of the same type. Then we don't need to make translations between the different frames and so forth. We can use the same frame structure. And then bridges can work on the MAC layer. And such a thing would look something like this. So instead of going up to the LLC, we basically just go over to the, like this. Okay. Questions, so forth? Okay. So we need these link layer bridges when we have two different technologies here. If we have the same technology on the two LANs, we don't need to go over the link layer. Yes?
Yeah, an overall question. When it comes to like the Ethernet, which are like a bunch of different versions of it.
Yeah.
Do we need to know them all, or like the exam? Or how low do we need to go in the abstraction level?
So what comes on the exam is the question. No, so I'm not so focused on the different details in the different Ethernet standards and so forth. You need to know that there is one 802.3 and one DIX Ethernet. So this is what you need. You don't need to know all the variations of Ethernet. Only that there are. Okay. So I'm not going to ask, for instance, what type of fiber is used in this. I'm not going to ask that. Yeah. Okay. LAN bridges. Here, these LAN switches, when you connect them together, the end devices don't know about them and don't care about them. They just do their job in the silent. Okay. So let's see how this magic works. How we can just connect switches together and get the functional network without a lot of configuration. So what we would like to achieve is something like this. So we have here a LAN with a number of n nodes, and we have a LAN 2 with a number of n nodes, and we want to connect the bridge between them such that the nodes which are connected to the upper LAN and to the lower LAN sort of sees like they're connected to the same LAN. So this is what we would like to achieve. And we would like to do that without these n nodes have to configure the bridge node or somehow be aware that the bridge node exists. Okay? And this can be done in a very smart way. And maybe we just look at the example here and illustrate what the problem is. Okay, so suppose we have this situation where we have a LAN here, a LAN here, and a LAN here. And we have, in this case, 5 nodes. It could be many more, of course. What we would like to do then is to enable connectivity between all of these. So how's that going to work? Well, a bridge, B1 here, has 2 ports. It could have more ports than 2, but in this example it only has 2. It has this port and this port. And it also has a forwarding table here that tells us addresses on this, and these are MAC addresses, and then to which port these frames with these MAC addresses should be forwarded to. So when B1 hears a MAC address, which is in the table here, it knows to which port it should send it. But how does it know how to fill out this table? Well, at power up, it knows nothing, so the table is empty. And B2's table is also empty. So what's going to happen now? Well, suppose that S1 would like to transmit something to S5. Happens to be on 2 different LANs here, but S1 does not know about this. Okay, the first thing that happens then is that S1 sends out a frame that says, okay, I'm S1, this frame should go to S5. So what happens then is that this is transmitted, oops. It's transmitted over this LAN, and it's picked up by the bridge. Okay, and the bridge says, okay, so this is a frame from S1, it should go to S5. Where is S5? It looks in the table, it says, I have no clue where S5 is. So I'll just send it out on the next port here, because maybe it's here, maybe it's not, I don't know. But to be safe, I just send it out here. But at the same time, I know now that S1 is on my port 1. Why is that? Well, because I heard something from S1 on my port 1. So I know where S1 is now. Good. I have no idea where S5 is, but I'll just transmit it out on all of my ports. Okay. So the next thing to happen is that this frame goes out onto this LAN, and then it's not picked up by S3 because it's not destined to S3, but it picks up by this bridge. So this bridge says, okay, it needs to go to S5. I have no idea where S5 is, so I just send it out on all my other ports, which is on port 2. But I also know that S1 now is on my port 1, because that's where the frame came from. So bridge number 2 can put in that S1 is on port 1, my port 1. And then the frame is sent out and delivered to S5. Okay? So even when the table started to be empty, the frame can actually go all the way it needs to go. Okay, good. So what happens next then? So maybe S3 has something to send. S3 wants to send to S2. So he puts out this frame from S3 to S2. The frame is picked up by both bridge 1 and bridge 2. So if we look at bridge 2, it says, okay, something from S3 needs to go to S2. I have no idea where S2 is, so I'll just transmit this out on this LAN. Maybe it's here, maybe it's not, I don't know, because S2 is not listed here. But now I also know that S3 is on my port 2. S3 port 2. Bridge 2, same procedure. It knows now that S3 is on its port 1. Okay, and then this frame is then forwarded out on the output ports. This frame here will die because nobody will pick it up, but the frame here will be picked up by S2. Okay, so we can still connect. And then maybe S4 needs to be sent to S3. Okay, so S4 sends out the frame from S4 to S3. B2, look at this, okay, from S4 to S3. Do I have S3 here? Yes, I do. I know it's on port number 1. So this one needs to go out on port number 1 for sure. I know this. And also, I know now that S4 is on my port 2. Okay, and then this goes out like this. And then, of course, is picked up by bridge number 1 here. Says that S4 to S3, but bridge number 1 knows that S3 is on port number 2. So he knows that it needs to do nothing with it. So he will not forward that frame, right? It's not needed. But then it learns that S4 is on its port 2. So here, by listening to the traffic, the bridges can figure out where nodes are. Right? And keep on going like this. Okay. So a few seconds and we're done for today. So this adaptive learning works well. And in static networks, these tables will then eventually store all addresses and then learning stops. However, in practice, stations are added and moved around all the time. So there is some timer expiration of these entries, and every now and then the switch forgets its entries in the routing table, forwarding table, and then this needs to be learned from anew. If a frame, for instance, arrives on a port which is different from what is expected in the entry of the table, then this is updated immediately. Okay, I think we stop here today, and then next lecture we will talk about one problem that occurs when we have these type of switching networks, and then is when we have loops in the networks, and we need to deal with that also. And once we have figured that one out, we go for Wi-Fi. But that's all for today. So thank you.